Hi, my name is Jonathan Hawkins, and today I will be talking about wingtip devices. Wingtip devices aren't a new technology, but they're emerging in the aviation field because of their uses to improve efficiency in jet airliners and other fixed wing aircraft. They improve the efficiency by three ways. The first is to increase the aspect ratio without increasing the horizontal wingspan. The second, they add a thrust vector. And third, they decrease wingtip vortices. Aspect ratio. The aspect ratio is B squared over S, which is your wingspan squared over your area. Now, your regular wing without a wingtip, this would be your wingspan, V, and your area is the shaded region. And this would be your S. And when you have a wingtip applied, your horizontal wingspan stays the same, or generally about the same length. It probably only extends about a foot to 5-6 feet, but your actual wetted wingspan, which includes all of this area, well, this length, increases. So this B increases, and that increases your aspect ratio. Now, aspect ratio, when your aspect ratio increases, your induced drag decreases due to the longer area of your wing, and that can be shown in the drag versus velocity diagram, which shows that your induced drag decreases as your velocity increases, but your profile drag or your form drag increases as your velocity increases. And when you add those two drags together, you get a total drag as such. So this will be your induced drag, and this will be your form drag. And as your induced drag decreases for any given velocity, when you apply your wingtip increases your area, so therefore it increases your form drag or your skin friction drag, because there's more area on the wing for interference and the air to flow over. So your form drag increases, but only marginally compared to how much your induced drag decreases. So that's one way that it increases efficiency on your aircraft. The second thing is your thrust vector. Now, when wingtips are designed, they can be designed in a certain way that your, and this is from in a top-down view, that when your velocity from your wind is coming in at a certain angle, it produces a lift, a component of lift due to the wind, and that in turn has thrust going in the direction that you're also going, which would be this. So this would be your thrust vector, and that also increases efficiency because of the added thrust. Now, the final way that it increases efficiency is due to the decrease in wingtip vortices. Now, wingtip vortices are caused by the tendency for air on the bottom side of the wing on the higher pressure side, because as we all know, in an airfoil, when air is going around the airfoil, the top air is moving faster, therefore it has a lower pressure, and your bottom air is moving slower, which means it has a higher pressure. Now, in a 3D airfoil, in a 2D airfoil, there is no spilling. But in a 3D airfoil, there's a spilling from this high pressure on the bottom wing, on the bottom side of the wing, and your low pressure on the top side of the wing, and it tends to, the air on the bottom side of the wing tends to spill over on the top side of the wing. Now on wings without winglets, this effect is great, and it causes very large wingtip vortices which slam down onto the wing and cause a reduction of angle of attack and various other things that slow down your aircraft. Now when you have a wingtip device added to your airplane, and there's many different types of wingtip devices, this effect is minimized because you're stretching, you're taking your, there still are wingtip vortices at the tip, but they're greatly reduced because of your increase of your aspect ratio and the fact that they're farther away from the actual wing and control surfaces. So there's less likely of a chance for this to interfere with anything.